All right. Well, now I'm really excited to introduce Carolyn Yackel, who is a professor at Mercer University and a mathematical fiber artist, known primarily for her work in Tamari, but also work with knitting, shibori, and other media. Her book, Figuring Fibers, is a gorgeous exploration of the intersection of mathematics and the fiber arts. It's both accessible and rigorous. It has projects. It holds a treasured spot on my own bookshelf, and I'm really excited because she also recently announced the arrival of a peer-reviewed journal at the intersection of mathematics and the fiber arts called Interlace. So that's very exciting. Maybe we'll hear more about it today. Either way, I'm very thrilled to introduce Carolyn Yackel.
Thank you very much. And I just want to thank the organizers for this opportunity to be here. And also I want to thank everyone who's here for coming to the talk. So the title of my talk obviously is Marrying Mathematics with Illustrative Techniques. And so I just want to tell you, this is something I've been thinking about for a long time. And so we'll see how it goes. Maybe I'll have things that you want to say about it too. So, but before I start the talk, actually, I did want to talk about Interlace since we just launched this journal. This is a peer-reviewed open access journal that I just started with Sarah Marie, or really I should say Sarah Marie just started with me. She's like the driving force, really. It's focused on mathematics and fiber arts, and you can get the QR code right here. Or if you want, you can just like type this into your browser. But please send us your good mathematical fiber arts work. We're hoping to publish our first issue in April. Okay, so, wait, I want to, yeah, there we go. So, I'm reminding you, even though I just said this, the title of the talk is Marrying Mathematics with Illustrative Techniques. So what does that even mean? It can mean that when you're using a specific artistic technique, you model it with just the right mathematics. It can also mean that when you're trying to depict a mathematical idea, you need specific techniques. So I'm going to give a bunch of examples with some excellent alignment and some with imperfect alignment between the mathematics and the techniques so that we can consider what works well and what can be better. And also we might decide that sometimes a lack of alignment in one aspect helps to highlight that specific mathematical aspect for the viewer. But the thing is that while that might really help highlight that aspect, it can also be really jarring. So it might not be what we want in our art, but like just for our friends, like maybe that's really helpful. Okay, so the first thing I want to talk about is ceramic tiling. And I'm just showing you right here how it's been grouted. So this is like, notice we need grout. So in my first example, I have a ceramic tiling on the left and a digital tiling on the right. And the reason I have this is I wanted to make a rep tiling because I went to this really awesome talk by Chaim Goodman Strauss in like 1999. And he had this really cool picture of this L tiling. So a rep tiling is a, a tile. Well, a rep tile is a tile that will tile itself at a different scale. So on the right here, you can see that 4 of these green tiles will tile one of the brick colored tiles. And so I thought about it for a really long time, and then I was like, I really want to make that in ceramic. So I wanted to make these tile tabletops, and it just so happened that I started looking at it right around the time of Gathering for Gardener 9. And it was really cool because it turns out that not only can you 4 tile an L tile, you can also 9 tile an L tile, which is what's going on here. So there are 4 layers of 4 tiling in this part right here. And there are 3 layers of 9 tiling in this part right here. And you can imagine why there are 3 layers, because you just have to make so very many 9 tiles to make a 9 tiling. Anyways, okay. And you can see that I made this digital layout for myself so I'd know what to do. And then I didn't exactly follow it because it's just like too much. But what I'm trying to point out to you here is the grout problem. So what happens is you're using your digital tool, like I was using Illustrator, but you could use Inkscape or whatever, and you make like this piece right here, which is your four-tiling, and then you shrink it down a size, and you want to just lay it over to make your digital tiling. But when you shrink it down, the grout size changes. And if you look
Oh,
carefully, yeah, exactly. And so, and so you can see that that happened and it looks kind of bad. And that also happens on the left when you're tiling in ceramic. And somehow, even though I'd done this digital tiling, it just didn't even get in my brain. So I was like, oh, this is bad. And then I would just highlight the whole thing and then I'd change the border size. But when you're doing it in ceramic, you can't do that. So I just realized that there is this issue. And then when I talked about it at Gathering for Gardener, all the digital people were like, yeah, of course, we all know this happens. So like one thing I want to talk about is like, for one thing, it's really cool because you can talk to people who work in a different medium and they'll be like, yes, we know about this problem. And maybe they have a solution, or maybe they know that there's no solution. But also you can see that there are these problems that actually maybe are insurmountable. So it could be that quilting would be a way to deal with this, because you actually need to show that there's a distinction between these pieces. Like all of these should kind of be the same color, so you need to show there's a distinction. Maybe quilting with contrast thread might be really good because the contrast thread kind of has like zero width, but then it doesn't actually have zero width. So maybe it wouldn't be good. I'm not sure. So here's a different kind of solution that might work. This is a different reptile, but I made it in cookies. So that's kind of good, but then also there's a problem with cookies, which is that you have to keep making it. And that's also not as good. So I don't know. Maybe there's no real way to deal with this problem. Okay, so the next thing that I want to talk about is knitting. So if you don't knit, then hopefully it won't bother you too much that I'm telling you how knitting works. Like maybe you don't know this. So if you do know it, just please forgive me. Okay, so the way that knitting works is you make a bunch of loops and then you transfer these loops into another bunch of loops on the next layer. And so that's how this fabric is formed. And so if you're wearing something knitted, like actually I am too, that's what happened. That's how you got this knitted thing. Is there were loops and there were loops pulled through those loops and there were loops pulled, oh, sorry, loops and then loops and then loops and then loops. And that's how you got your knitted piece. Okay. And so the reason why I'm talking about that is because I want to actually talk about cross caps. So this is this really genius idea that Emily Peters had. So she was thinking about cross caps, which are really just a way of thinking of the projective plane living inside of R3. And so again, I'm just going to hopefully maybe this is more than you need to know, but maybe for some people here, it's not more than you need to know. So I'm just going to say it. So you can take a sphere and then you can identify antipodal points. And so in A, we just have our sphere. And then in B, we're identifying the antipodal points. And then in C, the upper part of the sphere has already been identified with the lower part of the sphere down here. So we're just going to not show it anymore. But we're still showing this part in the middle, okay? Because these points on the equator are still identified with the opposite points on the equator. And so what she decided to do is to arrange these points in the equator in a figure eight. Like, why did she decide to do that? I don't know, but she just did. And it's like a really good idea, actually. So she decided to arrange them in a figure eight. And when she did that, she pushed this half through to the other side. So she's like inverting this half. And when she did that, the front half of the bottom of the sphere had to be passed through the back half. And that's why it became blue. And so then she pulls the top, these two top circle parts, she just elongates them so they can come up and reach each other and then be identified together. And so that's what's being shown in this right-hand sequence of subfigures. So in a way, if we're just talking about illustrating mathematics, it's good and also not good because it needs words. But then on the right-hand side, that's all knitted. She comes up with a way of knitting this, which is really cool because the self-intersection comes naturally. So like this part in figure F, subfigure F, is the same thing as what you're seeing on the right-hand image, except upside down. So the self-intersecting part is the part at the bottom, and this smoothish part is the part at the top. But if I had turned the picture upside down, it would have looked weird, just because of the perspective. And so what you do is you knit this part first, and then you pick up the stitches in a figure 8, and then you just knit them in the figure 8 with your knitting needle in a figure 8. So because of the way that you're knitting stitches on stitches on stitches, it's okay. You can just knit that way. It's really, really smart. It was like so smart that she thought of that. So there are other media in which you can do this. Oh, I was going to say, by the way, if you know how to knit and you haven't done that before, I really highly suggest that you knit That Thing by Emily Peters. It's in, I think it's in Crafting by Concepts. So I really highly suggest that you knit it because it was such a smart idea. But you can do the same thing with 3D printing or crochet because both of them, in each of those media, you can lay down rounds of material. So that's actually been done before in 3D printing. Somebody has 3D printed a cross cap in exactly this way. I just found it on the internet. I don't have an image of it. I just have this image of laying down rounds of 3D printing. And as we know, like you can 3D print in other ways too, but this is one of the ways of 3D printing. But like, as you can see on the right, and these are just images that I grabbed from the internet, the way that you crochet, you're also laying down rounds. And so you definitely could crochet a cross cap in the same way. And I don't know of anybody that's done that, but you could. So somebody, go ahead, do it. So other people have tried to instantiate projective planes by making, for example, boys surfaces. So the left one is Claire Irving's knitted boys surface, which is really, really beautiful. And actually, I'm very lucky because she gave that to me. And it's nice because you can hold it in your hands and you can sort of examine it. But it's knitted, and so it's solid, you know? The one at the right is at Oberwolfach, and I just found that image on the internet. But one thing that's really nice about it is that it's gridded, and so you can see through it. So even though it's self-intersecting, you can kind of see the way in which it's self-intersecting. So you can see like the pros and cons of each thing. Okay, the next thing that I wanted to talk about was Tamari. So Tamari is like just another form of, well, it's another media form. It's another form of art, and not everybody has heard about Tamari, so I just want to tell you how you make it. So the one part that I didn't tell you about is how you get the inside. So the inside is just like some sort of core, and you want it to be kind of spherical. So you can start with anything, really. Like you could start with a styrofoam ball, but you could also start with a wad of paper or a bunch of dryer lint or any just kind of junk. I think it's traditional to start with rice hulls because they're abundant in Japan, and this is a Japanese art form. But anyways, you take your junk and then you wrap it in junk thread, like thread that you don't, well, junk yarn that you don't really want to use for something else. And then you wrap it in thinner junk yarn, and then you wrap it in thread. And this thread should be the ball base. And you can see that I just have different pictures from different things. So usually this yellow color would be the ball base, but then I used a different ball that I was using. So it changed to orange in this picture. But anyways, after this stage, then what you want to do is plot guidelines. And so the guidelines are these silver colored threads right here. And the purpose of plotting these or laying these guidelines is the same as like gridding out a large canvas. The thing is that tamari balls are typically they're typically stitched with a repeating motif, and the symmetry of the motif on the ball in the end is part of what lends it its beauty. And so if you do like a bad job on the symmetry, then it's like, oh, you did a bad job. So you kind of want that to come out really nice. And so you want to make this come out really well. So it's a good idea to plot it and be really careful about that part. And then at the end, you just stitch into that thread layer. You're stitching into this thread layer right here. And that's basically like your fabric. Okay, so when I started doing this, I realized that what was happening was I was stitching these dual platonic solids, basically the dual spherical platonic solids. And it's not just me, like everybody that makes these tamari balls that knows about platonic solids realizes this, and which is really cool because it means that that piece of mathematics really aligns well with what's going on. So I'm just showing the dual platonic solids over here. This is, I think from well, it's from Banchoff's website. And here they are on the tamari balls. So like, if you haven't seen this slide from me before, right here, if you look at this kind of star thing, there are 6 of them on the ball, and they're basically like the faces of the cube. And then if you look right here, that's more like the faces of the octahedron. Here on this orange ball, you've got 12 stars, and those are the faces of the dodecahedron. And these parts right here, there are 20 of those, and those are like the faces of the icosahedron. And this one is like the dual tetrahedra. So there are 4 of these triangles, and then there are 4 of these triangles, but they don't really look like triangles. So you just have to kind of shift your perspective. Okay, so because of that, I was like, oh, so what's really going on with this? And then I was reading the symmetries of things, and so much of mathematical art has come from the symmetries of things. So I really thank Conway, Burgiel, and Goodman Strauss for publishing this book, and really great thanks to Haim for making all these great photographs or really digital images. And so I was like, wow, I didn't even know that there were 14 discrete spherical symmetries. So I was studying his images, and I was like, I wonder if I can make them all in tamari. And so here's an example of this one, which is 432. So you can see this rotational center here, this 4-fold rotational center, this 3-fold rotational center, and this 2-fold rotational center. And I was able to make a tamari ball with those same rotational centers, and it's right over here. And the way that I was able to make that happen was by having weaving in my stitching. So you can see this weaving. And so one time when I was talking about that, someone pointed out like a really interesting and important fact, which is that I am thinking about the weaving, the over-under weaving on these threads, but I'm not thinking about the stitches right here themselves. And that brings to mind something that Susan Goldstein said once, which was really important. She was talking about knitting, and she was saying, when we look at knitting, sometimes we're thinking about the symmetry at the stitch level, and sometimes we're thinking about the symmetry at the pattern level. And the same is true in like a whole bunch of different crafts. We want to think about the symmetry at different levels when we want to consider, when we want to create different symmetries. So it turns out that I was able to construct balls with all 14 different spherical symmetry types. But like one thing that's true of these, you can hold them in your hands and you can turn them over just like Claire Irving's piece. But you have to trust me on the symmetry types. Like this, this kind of pink, well, it's actually pink, but it looks kind of red here. This one, you can't see what the other side looks like. Same with this one. So no matter what viewpoint you have, unless I did like a video, you couldn't tell what the symmetry type is. I guess that might be true of Heim's digital images too, but because they're digital and his whole point is illustrating, maybe it's you just believe him more. I'm not sure. Okay, so after that, I was asked to be involved in the Mathamalchemy project, which I don't know if you guys know about the Mathamalchemy project, but if you don't, you can look it up online. It's a really cool project that has so many different components with so many different kinds of mathematical art. So one of the parts of that project was to create these ball arches with like lots of wrapped thread balls. And then some of them were made into what they called embellished balls, by which they meant they were going to be embroidered in the Tamari style. And so we wanted to think about what should they be like. And so we decided to have them embroidered with the 13 Catalan solids. And so I was like, okay, well, let's have 3 different embroidering styles for these 13 Catalans. And so you can sort of see the 3 embroidering styles here. Oh, maybe we should look at this one. So like one of them is going to show the edges, and one of them is going to outline the faces. And then this one is just weird. It's going to, I wanted to take each face, and then on each face, I wanted to connect the midpoints of the sides. So then I'll show you, well, let me go back. So that's what's going on here, like with the distiascus triacontahedron. This shows that. And if you're like, what does the distiascus triacontahedron even look like? It looks exactly like the picture on the left. That's just a spherical version of it. And so if you're like, well, what would it look like if I connected the midpoints of the sides? It looks like the figure on the right. And then if you're like, wait, that doesn't look like the one on the left. You're so right. It totally doesn't look like the one on the left, which means that that this idea of connecting the midpoints of the sides was like a really bad idea. That wasn't a good stitching type at all to depict the distiascus triacontahedron. But sometimes when we're trying to depict something, we make a bad choice. Like artistically, we can make a bad choice. So I guess that's one of the things I want to say to you is like sometimes we just make an error. So mathematically, this is not the distiascus triacontahedron. What is it though? It turns out that it's the deep truncation of the distiascus triacontahedron. So like the first example that I gave you of the ceramic tile top, that was more like just an oops. Like that one, there's kind of no saving that. I do have those tables in my house and they're kind of pretty, although there's some flaws in them too. But this one is just like a mistake, but then it turns out to mathematically have meaning. It's just a different meaning than I intended. So it turns out there's like, it's salvageable. But um, going back, I just wanted to show you the status of my project that probably no one else cares about but me. But I'm really happy because I was making 39 tamari balls, and you might surmise this project started in 2019. And so it's been like kind of going on for a long time, but I only have 5 balls left to make. And so I'm pretty happy about it. Okay. So the next thing that I was going to talk to you about is Itajime Shibori. So this kind of shibori, it's kind of like tie-dye, okay? So the difference, I guess, between this and tie-dye is that you fold up your cloth, then you clamp it with these resists on either side, and then you dye it. And you can see me doing this. I've got my piece folded up. I've got there, you have to use a resist on both sides because otherwise the dye will get through from the side that doesn't have the resist. And then I'm clamping it with these binder clips, and then there's dye off to the right. Okay, so here's an example piece. What I had set for myself as a goal was to try to make all 17 wallpaper patterns with Itajime Shibori. So basically what I did is I started with a medium, this kind of shibori. And then I set for myself a mathematical task. So I was next being driven by a mathematical problem. But then what happened to me was I was just stymied by being unable to do it. And I was like, what is going on? So then the symmetries of things came to the rescue again. After thinking about this, for really a long time, I realized that what I was doing was I was folding my cloths into the orbifold that corresponded to the wallpaper pattern. And so this is an example right here of the Mobius. This is the wallpaper pattern that corresponds to the Mobius orbifold. And this is actually the same cloth. So because we have cloth, it's really not a good idea to cut it. Because if you cut cloth, it's going to fray and stuff like that. I guess you could get cloth that doesn't fray. But even if you get cloth that doesn't fray, if you want to mend the places where you cut it, you're going to use up a little bit of cloth in the cutting because you need like a seam allowance and stuff like that. And so it won't really be the same. So if you're using cloth and you're dyeing cloth, then there are really only 7 orbifold types that you can make, not all 17. So you lose, let's see, you lose 8 of the types because you can't have a cone point, and you lose 2 of the types because you can't fold them in 3 dimensions. Okay, but the thing is that later on, of course, it always happens to me later on, that I found out that Weihart had actually already done something like this using paper in a Bridges paper. Of course, because she was using paper, she could cut it. So she could get more orbifold types. The other thing that Vi did, which was so genius, was that she used beach balls in addition to paper. So she was making the orbifolds for the sphere, which it really seems very hard to me to figure out what to do when you have a sphere. But I put the link to her Bridges paper right here, just because I thought you would like to see it. I mean, it's really, really amazing. And probably some of you will get some beach balls and cut them. The other thing that I want to mention about Itajime Shibori which is really, it's really interesting to me, is that artistically, you have this lack of perfect control. And I really like this. So in the one sense, if we're trying to convey something with our mathematical illustration, which I think is the point, right? The point is to convey something to the viewer. Then this lack of perfect control is, it's like in opposition to that. But on the other hand, I think it's more artistic. So like when I really like this piece of cloth, it's really, I like it a lot. And it's a 442 or Befold, or I think it's P4M, right? But look, like down here, it looks more like presents. And up at the top, it looks more like flowers. So if you didn't know anything about wallpaper patterns or orbifold types, like what would you see in this? What are you seeing? I don't know. So that's just like a question that I leave for you. Like, is it good? Are we really wedding the math to the medium or not? Okay, so I think it's good sometimes when there are these mathematical limitations of the medium. I think this is really interesting. And I want to talk about it also just from the perspective of editing papers, because I think that one of the really hard things that happens when we write a mathematical art paper is we have to talk about this. So on the left is this really beautiful piece of cross stitch that Mary Shepard did. She was the first person to talk about how, well, the first person in the literature that I know about to talk about how only 12 of the 17 wallpaper patterns are achievable in media that don't admit 30 or 60-degree rotations. And because she talked about that, now everybody can just refer to her work. So then, like at the right here, you can see that as a result of that, Susan Goldstein was able to just refer to her work, but then she narrows that down to only 9 wallpaper patterns being achievable in double knitting. And Susan's done a lot of work just looking at what people have done in terms of making these samplers, where they look at all of the different possible wallpaper patterns achievable in a given medium, especially fiber arts medium. And then Susan and I looked at these, all the wallpaper patterns that we could get in mosaic knitting. Here's my little swatch on the left and Susan's amazing piece on the right. So we already knew there were only 12 potential wallpaper patterns from Mary's work, but when you look at the 2-color wallpaper patterns, only 22 are attainable in mosaic knitting. And then when you look at the friezes, there are 17 2-color friezes. That's just a coincidence. So there are 17 2-color friezes. 14 of those are attainable in mosaic knitting. And Susan's showing that in her piece right here on the right. Okay, so those are my examples for you today. I went a little bit fast, but my last slide is just another announcement. I bookended my talk with announcements. And so I think at least once, but maybe twice, I mentioned Gathering for Gardener. So the 16th Gathering for Gardener is going to be held in San Francisco. And please, if you would like to come, notice that registration is already open. And Gathering for Gardener is a really great place to go if you're interested in mathematical illustration and especially mathematical exposition. So if you have gone before, please sign up again. And if you want to be invited, you can self-nominate for an invitation. So please do that. Okay, so like I said, I know I ended really early, but please talk about what you would, how you see mathematics aligning with illustration, and how you, what problems you're having with your mathematics aligning with illustration. Thank you.
Thanks so much, Carolyn. That was a gorgeous talk. Judging from how the chat was blowing up throughout, I think many visitors agreed. Yeah, we do have a few more minutes. I'm wondering if folks wanted to hop in with questions. I could also rebound some from the chat, but feel free to unmute yourself and ask a question if you'd like. Cool. Well, George in the chat did ask a question, just asking if you're familiar with Diana Taimina's work, which
Yes, I was going to add a whole thing about the hyperbolic planes actually, but I didn't. I should have, because I had plenty of time. So yeah, I think hyperbolic planes are like a really great place to look, because there are so many different ways of looking at hyperbolic planes. So Dinah, you know, she's such like the quintessential example of coming up with a really good way to visualize hyperbolic planes. And yes, but then there are these other ways, right? So people started by putting together these annuli. Do you know what I'm talking about? So they would tape together annuli and then make models of hyperbolic planes. But there are also these, I think they call them like soccer ball models of the hyperbolic plane. And it was Dinah's son who came up with that model. So you, I don't, the reason why I didn't put that in here is because I think I threw my models away, but I used to have a whole bunch in my office, which I could show you. And they're really fun to make. I really suggest that you do this. You can find these paper pieces online and cut them out and put them together. And so, yeah. So the thing about the soccer ball model is that you leave like a heptagram blank in the middle. So there are like all these hexagons and you leave like a heptagram blank in the middle. I think that's right. And then you have the annuli that like has a different problem. And then when you make your, I can get some of these, hang on one second. Then you have your Dyna type models here, which are really good. And the great thing about Dyna's model is you can, sew on it and put on your lines, for the hyperbolic plane, and you can see your geodesics. And so those are really great. And you can use them with students, and students can make them. And you can make them with different curvatures, which is really great. And somebody else made this one because it's really tightly done, just like her models. Mine are really floppy. Yeah, and Erin, haven't you made hyperbolic planes out of something like latex or something?
We did manage to make small patches of paper that is hyperbolic
Yeah.
back at ICER. Yeah.
Yeah. They don't take too long. I've done it with students in a biology class, and they're really interesting. They're fun, and you just like, it needs lots of tape.
Yeah, the one of the big challenges for us was getting sizable patches, right? We could get small ones, but it was hard to scale it up for obvious reasons, I guess.
Yeah. Well, it's actually pretty good to do with like a classroom of students, because you can have a bunch of different tables doing little pieces, and then they put them together and it gets pretty big. And I should mention here too, Henry and Sabetta's VR model. That was another model of hyperbolic space that I was going to put in, and I think it's really interesting to look at that, because I mean, it's part of why I did and didn't want to talk about it. Because like if I look at this, I get a sense of what's happening. And when I go into their VR model, I totally don't understand what's happening. Which I think is a good point, because that's why we need more than one representation so that we can get lost and try to figure ourselves out again.
So awesome. A lot of folks in the chat are also sort of like talking about different things you can do with hyperbolic geometry. I like Gwen's idea of sort of weaving hyperbolic tilings using bead weavings into some of these crocheted models as well. It seems
That's right. So Susan Goldstein had a beaded hyperbolic plane.
that's awesome. I also just wanted to bounce Saul's comment, who was asking for if you could share a link to the pattern for this sort of cross-cap projective plane. I'm wondering if there's a pattern there somewhere.
That is in I
It's
think
in one of the books.
yes.
Okay.
I don't think I can share a link, but I'm pretty sure it's in this book here.
Great. Thank you. Are there any other questions floating around?
I had a quick question about the a quick question about the wood resist dyed Mobius strip propofol, which is how did you join that into the Mobius strip sort of ball that was pictured on the right?
Oh
Like it
yeah.
didn't.
You just do it. Yeah. This is what oh, this handkerchief isn't that clean. Okay. It just has lipstick on it. Okay. So you just take your handkerchief, right? And then okay, so you take your handkerchief and then you accordion fold it. You can do this at home, okay? You take it, you accordion fold it, or whatever, you can take any cloth you want. And then if you're gonna actually dye it, scour it first so that the stuff really sticks. And then, okay, now you need it to be long enough so that it's thin enough. You know what I mean?
Yeah.
Like with any Mobius band. Now the middle's already marked because it's been sitting around. Now you just make it in, look, see how I'm making it into a Mobius band? See what I mean? Okay, now just follow it around. Just follow it around with the other.
Hmm.
Oh, so it's like if you really wanted to join it end to end, it would self-intersect, but from the point of view of dyeing, it doesn't matter whether it actually
It
self-intersects.
doesn't self-intersect.
Again?
I'm just following it around. Look,
Okay.
it's a Mobius band to the middle.
Oh, I see.
And now I'm just following it around with the other half of the material. You have to like
Yeah, okay.
push it. You have to push it.
That's really cool. So it's like, so just to repeat back to make sure I understand. So it's like you're making a Mobius band, except the end of the strip would be joined to the middle, and then you sort of double it by following it around.
It's a double cover of a Mobius.
Yes. Awesome. That's really cool.
And Aaron, you don't have to use wood resists.
Right.
You can use anything. I used coins. I used washers that I got from the hardware store. And then George Hart was like, "Oh, hey, can I cut some little plastic pieces? What are they called? Latex? No, it's not latex. What is that stuff?
Acrylic?
Acrylic pieces for you.
Oh,
Those are the best. Oh my gosh."
that's cool. Okay. I'll ask more about this in the Discord chat. This is interesting. Although I also it's a bad temptation to get dye all over my house.
No, do it outside.
Yeah.
Cool. We're at 102, so maybe it's time to say goodbye for the week or month, I suppose. But Discord is still well, it's still flowing. There's more folks asking questions and chatting, and so feel free to kind of check into the various threads. And I'll hand it back to Aaron to sign us off for the day.
Yeah, thanks, Gabe. Thank you all once again for coming, and thanks to our three speakers. It's been another delightful hour. And do tune in next month. We are meeting next month. And as Gabe said, feel free to continue on the Discord as long as you want. And we'll see you next time. Thanks, everybody.